So in the last set of notes, we defined our Eulerian trails and circuits, and now we're going to talk about that a little bit more. So if we're going to cross each edge exactly once, then we need to think about the degree of our points. If we're going to cross each edge exactly once and return to the start, well, if I think about edges, edges connect two different points, or if it's a loop, it connects back to the same point. So that connection means that I have to have an odd degree to connect 2 points. If I'm then going to come back at some point, I have to have even degrees. So Eulerian circuits have to have all vertices with even degree. So this moment you have an odd degree vertice, you don't have an Eulerian circuit. It's not possible. If we have an Eulerian trail, we're going to have exactly 2 of our vertices with an odd degree. And I'm going to leave that proof to you. It's also in your book, and it is something that you should read through. But let's put this into practice by looking at example 1. So show the graph is semi-Eulerian. So I'm going to put my degrees for each of my vertices. So degree of A, 1, 2, 3. B is 2. C is 4. 1, 2, 3, 4. D has 1. And E has 2. So 2 of my vertices have odd degrees. So therefore, I must be able to find an Eulerian trail. And let's look for one. So I'm going to highlight it in orange. So we pick an odd vertex to start with. So I'm going to start at D. So I can go from D to C, CBA, back to C, down to E, and back up to A. So to be an Eulerian circuit, I have to touch every edge exactly once, and it doesn't matter how many times I touch vertices. So an Eulerian trail, I went D to C, B, then A, back to C, down to E, and back up to A. And there is multiple in this graph. So show the graph is semi-Eulerian, exactly 2 odd vertices. I'm going to leave example 2 up to you, determining whether these graphs are Eulerian, semi-Eulerian, or neither. You can check your answers online. And of course, see me with questions.